we still cannot place S0 with the updated T, so we shift upwards, we still cannot place it. We shift to the right and we update T, we cannot place it. We shift upwards and then we can place it here. The amount of shift is 6 upwards, so T becomes 2 and 6. Now we can place S1 and S2 with the same T, so we can place piece and we can update this strip. As you saw, we could just with a few tests, we could find the place of the piece on the strip. Now we can start the placement of another piece. So if the another piece is the copy of already placed piece, we do not need to start from bottom left corner of the strip, and we can start from the translation vector of the previous piece, which is 2, 6. Okay, now it's time to show some results. We did our implementations in C++ using Qt environment. We did our tests on a single core of a laptop with this hardware information. We are going to show the results for Han and Poly5B datasets. As you see in the table, we did our tests both with without rotation case and with rotation case. We first compute a base resolution for without rotation case, as you see in the column. And for getting a better quality, we do test with a finer resolution as well. So as the resolution gets finer, the use length of the container does not get better necessarily. And this is because of the simple bottom left heuristic that we are using. However, as the resolution gets finer, the time increases. Going from resolution from 1 to resolution 0.1, the time does not increase with factor of 10, and the time increases with a factor of 7. As we have more rotation, we expect that the quality of the results get better. However, we expect that the timing also increases. For example, we can have a look at delta theta equal to 45 degrees. This means here we allow 8 rotations. We first compute base resolution considering all rotated pieces, and then we again do the test with resolutions finer than base resolution as well. But how we compute it? During the placement, we consider the placement of all angles, and the final placement is done with the best angle. All the tests for delta theta equal to 45 degree was done in the time 10 to 40 milliseconds. And the best result was found when we used resolution 0.2 and delta theta equal to 90, which is 65.8, and the time was 10.1 milliseconds. And this is the best result that we found for Poly5B dataset. The same applies for Han also. So we did without rotation and with rotation. The best result was found in resolution 0.1 and delta theta equal to 45 degree, which is found in 9.9 milliseconds. And this is the best result for Han dataset. Okay, we tested the scalability of our algorithm as R changes and also as the number of pieces changes. In the first test, which is the left test, the execution time increases less than linear in 1 over R. So when 1 over R changes from 1 to 8, which is a factor of 8, the time changes from 1 to 6, which is a factor of 6. In the second test, we did the test with datasets with identical pieces. So the purple graph shows the result when we do placement each time from the bottom left corner of the strip. This is the extreme case that can happen for the dataset with identical pieces. Here, the execution time increases super linear, but it's still less than quadric in number of pieces. In the red graph, it's showing the placement with optimized methods. So the placement of each piece is happening with the translation vector of the previous piece. So when the number of pieces double, the time just increases a little bit. Accuracy increases as the resolution gets faster. However, this increase in the accuracy is not continuous. For example, when we go from resolution 0.5 to resolution 0.2, the use length increases a little bit, and this increases because of the simple bottom left heuristic that we are using. We compared our results with Burke's paper, which was published in 2006. We compared with this paper because it is using continuous representation. However, placement positions are on a set of equidistant vertical lines. So the quality of the placement depends highly on the resolution. And on the other hand, they also provided the results for a single bottom left placement. They provided the timing for single placement. However, unfortunately, they didn't provide the quality of the placement for a single placement heuristic. So we decided to compare our timings with this paper. One might say that, okay, comparing the results that you had with current processors with the results that were simulated on computers 15 years ago is not fair. However, if you have a look at the time differences, you will see that it's not just because of hardware performance, it's also because of the algorithmic performance that we have. At the end, I want to just go to conclusion. So the algorithm was fast and scalable as R and number of pieces changed. So it can make a good balance between accuracy and computational complexity, and it can be an efficient building block, and another meta-heuristics can be built on top of it, because most of the meta-heuristics do not depend on the algorithm and the representation. And they, for example, they work with the ordering of the pieces to get a better quality. The works in progress that we have, we are implementing meta-heuristics on top of the building block we have. And we also implemented parallel algorithm. We have an efficient parallel algorithm, and we have the results. However, for the sake of explanations, we just decided to go for the results on a single core in this talk. Thank you very, very much for your attention. And if you have any questions, I'm pleased to answer.
Thank you, Sahar. It was a really nice presentation, and we still have time for questions. José Fernando.
Thank you, Sahar. It was a very good, very nice talk, and very good ideas. I just have one question. Have you tried to use a kind of iterative value for the granularity of the discretization? Meaning starting with a larger granularity and then starting to be more accurate during the search. As you are now looking at more sophisticated approaches, in the sense that you have a search process over it, do you have thought about that?
Well, because resolution can change like non-continuously, so we decided to start our test with the base resolution we have. So the results which were done with the results with the test with resolutions larger than base resolution really are the results that are not acceptable at all. So we just decided that base resolution is a really good starting point, and we can then, for getting even better quality, we can go for the resolutions smaller than base resolution, and that's why it was a good starting point for us.
I agree, but the idea is in the same run of the heuristic or meta-heuristic or search procedure, you could start with a larger zone, then starting to increase it to be more detailed and see if you can get this idea. It actually is very old, because the first approaches for irregular packing were surrounding the piece by a rectangle, placing rectangles, and then we would see. So I think that in this case, it's more or less the same idea, but with the advantage of starting from the beginning with something that's more irregular. That's just a suggestion to explore, because it may provide very good results. Once again, congratulations, very well.
Thank you very much.
Okay, we still have time for one question. Okay, Julia.
Thank you, and thank you for the talk. It's really interesting. I wondered whether, instead of or as an alternative to bottom left, you considered any other ways of improving the heuristic. So it sort of looking at your diagram with the red lines where you can't place pieces, it seems that these could be translated into interesting search points if you were looking at moving pieces within an already constructed layout. So I don't know if you considered that approach at all.
No, we haven't done that test, but we did some improvements on top of the bottom left that we used. For example, the order of checking the order of the segments does not need to be from left to right, and we can do it like from first one, then last one, then middle one. This increases the efficiency of the algorithm, and we did some other improvements also, but it was just with bottom left heuristic.
Thank you.
So I think there are no more questions. Let's move on to the second talk. That will be me. Okay, I'm going to share my screen. Okay. Can you please confirm that you are seeing my presentation? Okay, thank you. So, my presentation, it is about a general mixed integer programming model for the rectangular guillotine cutting problems. And this is a joint work with José Fernando Oliveira, Leandro Mundin, and Maria Antónia Carravilla. My presentation is mainly divided in 5 parts. I will start by the problem definition. We will solve the single knapsack problem. In this problem, we have a strongly heterogeneous set of small items that have to be placed into a large object. The items are all different. This means that the demand is equal to 1. And we have a value associated with the items that can be equal or different to its area. So we have a set of items that should be cut from a large object, and we wanted to maximize the profit. And besides, the problem that we are dealing is a guillotine one, which means that the cuts that are performed on a rectangular plate are a guillotine. They go from one side to the other side, and we are considering the end stage problem. So we are not going to limit the number of stages. In this example here, we have a first stage vertical, a second stage horizontal, a third stage vertical, a fourth horizontal, and we would require trimming cuts to separate items from waste. So this is the problem that we are going to solve. And for that, we are going to propose a new mixed integer programming model. And the model is based on assumption that given a rectangle M that have a length and a width, 2 types of cuts can occur. We can make a vertical cut, and from this vertical cut, 2 subrectangles will appear. A left subrectangle that we will index by M plus 1, and the right subrectangle that we will index by M plus 2. And these subrectangles will have the sum of its length, which will be equal to the length of the father subrectangle, and they all have the same width. The second type of cut that can occur is an horizontal one. And if we do that, we will have 2 subrectangles, one top subrectangle with index M plus 3, and the bottom subrectangle with index M plus 4. And we will have, all the rectangles will have the same length, and the sum of its width, which will be equal to the sum of the width of the father subrectangle. So if we represent this in a root, in a tree, we will have the root as the first rectangle, as the initial large object, and from that we will have left, right, top, and bottom subrectangles. And from this subrectangle, we can have again left, top, right, and so on and so on. So based on these assumptions, we will define our decision variables. So given a rectangle or subrectangle M, what we can do is to cut it vertically. So we'll have a xj variable indicating if that rectangle was cut vertically. In the same way, we will have yj variables indicating if that subrectangle is cut horizontally. And we have a third option is that we are not going to cut the rectangle, but we are going to assign an item for it. So this will be the delta ij variables. And also we will need the variables that are going to be used to define the size of the subrectangles. For the model, we also need the representation of the indexes related with the sons or the children of the subrectangle that we named it as left, right, top, and bottom. So in here, consider that the 0 represents the initial plate. So if we cut the initial plate, we will have the subrectangle 1 related with the left, 2 to the right, 3 to the top, and 4 to the bottom. So if we cut again subrectangle 1, we will have 5 as left subrectangle, 6 to right, 7 to top, and 8 to bottom. And the same happens for the second subrectangle. So we can represent the children, the left, right, top, and bottom, by these expressions, multiplying 4 times j plus 1, 2, 3, or 4, depending on the subrectangles. So with that, we can have a subrectangle index. With an algorithm, we can identify if the subrectangle is of type left, right, top, or bottom. And in the other way around, we can, for a given j, know who was the father of that subrectangle. So given that, in our model, we have as an objecting function, we want to maximize the value of the items that are cut from the large object. So we have the value times the assigning of the item to a subrectangle. We have to ensure that in a given subrectangle, only 3 situations can occur, or it is cut vertically, horizontally, or an item is assigned to it. We have to ensure that if an item is assigned to a subrectangle, it can only be if it fits geometrically. And for each subrectangle J, we can only assign 1 item. And we start by saying that the 0 is the initial plate. So the constraints are related with the vertical cuts. So if we cut vertically a subrectangle, we have to ensure that the sum of its length is equal to the length of the father subrectangle, and that therewith it is equal. In the same way, if we don't cut a subrectangle vertically, you will not have sons on the left and on the right. In the same way, if we perform an horizontal cut, we will have subrectangles, and its width of the subrectangle's children, so the top and the bottom, should be equal to the width of the father, and their length should be equal. Again, if the cut is not performed, we will not have subrectangles on top and on bottom. And so our decision variables are binary regarding the cuts and the assignment of the items to the large objects. And for the size of the subrectangles, we have real variables, positive. Okay? So this is the model for the single knapsack problem with a limited number of stages. And we thought that we could extend this model. And the first extension that we have done is related with the number of stages. And we can easily do that by identifying in each subrectangle the number of stages that were required to get to that subrectangle. So if the value is greater than the stage that we are defining, we remove these variables from our model. So we can have the number of stages fixed for the model. Another extension is, instead of considering that the demand is equal to 1 for the single knapsack problem, we are dealing with a single large object placement problem. So we have weakly heterogeneous assortment of items, and the demand is greater than 1. So what we will do is to select a set of items and assign it to the large object. And another extension is to consider that the demand is infinite. So it is the maximum number of times that one item fits in the large object. And so what we have done to the model, it was instead of considering just one item per subrectangle, we have a new set of variables that we define by kEdge ij, which is the grouping rectangles horizontally. And we can also make the same for the vertical organization of items. So if they are placed on the top of each other. And so we have to ensure that for a given rectangle J, we will only have kEdge or kV for the assignment of grouped items. So the model was updated. In the objective function, we still want to maximize it. In each subrectangle J, we must ensure that or we cut it or we assign items. And if we assign items, we have to ensure that we respect the demand. And of course, we need to ensure that they fit in the subrectangle. And once again, only one type of grouped items can be assigned to J, or horizontally grouped or vertical grouped. And in our new set of variables, we have to consider the new variables that are integer. And the remaining of constraints related with the vertical and horizontal cuts are also considered in the model. So after defining the model, we went for the computational experiments. And as I was explaining, we have different variants for the problem. And we use this representation for the different variants. First, we define the number of stages. Then we look to the orientation of the items and then to the value of the items. So the first set, we define that we have unlimited number of stages, that the items cannot be rotated, and that their value is equal to its area. In the second one, we allowed the rotation of 90 degrees of the items. In the third one, we considered only two-staged patterns with trimming, okay? And we have a fixed orientation of the items and the unweighted value. Then we have unlimited number of stages, fixed orientation, and the weighted value for the items. And since we are considering three different types of problems, we are considering the single knapsack, the slope, and unbounded slope. So with this combination, we end up with 12 different problems. Okay, so we are going to test on our model in these 12 different problems. And mainly we divided our computational experiments in two groups. The first group, we wanted to analyze the performance of the models considering the same set of problem instances according to the problem variants. Okay, it's not the same set because we need to update it considering the type of problem that we are dealing. Of course, if we are dealing with the knapsack, the demand will be only one. Okay, so we adapt the instance accordingly to the type of problem. And then we wanted to compare our results with the state-of-the-art methods from the literature. We use CPLEX 12.7 and we consider a time limit of 1 hour. So to the comparison of the model in the different variants, we selected 11 instances from the literature for the weighted slope problem. And these instances were selected as they are used at least 3 times in papers since 2016. And these instances for the weighted slope are the most complete ones because they have the length of it, the demand, which is greater than 1, and the value that is different from its area. So the first set, the CG cut, is from Christoph and Whitlock, then Ife and Roy Carroll, and the third one is from Feckett and Scheppers. So, as I said, we will going to adapt these instances depending on the type of problem that we are dealing. So for these 12 combinations, what we have here is the percentage of optimal solutions and the percentage of gap. As we can see here, the single knapsack was not so good, so we did not get a lot of optimal solutions, but what we got is that the gap is small. So maybe these solutions were already optimal, but the solver was not able to prove it. For the slope problem, also it happens for the infinite number of stages fixed and oriented and weighted. And for the 2-stage, we also have a small gap. So maybe these are near the optimal. For the U-slope, it was the one that we got best results. We got a higher number of optimal solutions, but we are not able to find any optimal solution for this case here. Okay, as we can see that the gap is high. Regarding the average occupation, we can see that we are near they are well occupied. And regarding the times, as expected, since we didn't prove the optimality, it means that it requires the time limit. And for the U-slope, we got smaller average time, so we could prove optimality before the time limit. For the comparison with the different, with the state-of-the-art results from the literature, we compared for the single knapsack with Forini and Martin. And these times and values were directly taken from the original papers, okay? And as we can see, for Forini, we only got one optimal solution. We were able to optimize, to get optimality in all problem instances. Comparing with Martin, we also have good results and the times are similar. For the version with 2-stage, we also compared with Martin 2020, and they were not able to prove optimality in 3 instances. We could do it for all of them, and the times are similar. For the slope, we compared for the infinite number of stage fixed and weighted with Forini and Ushio and Velasco. In this case, we only got 5 optimal solutions, but even in the time limit, the gap was really small. This is in percentage, okay? This is the average. The same happened for the other version compared also with Velasco and Ushio. We only got 2 optimal solutions, but once again, the gap is really small. And for the 2-stage fixed and weighted version, we compared with Lodi and Monacci. And this, in this case, we only got 12 out of 24. And in this case, also the average gap, it was also small. For the first state that we use in the beginning, we compared with Forini. And in this case, we got 4 out of 11 optimal, and Forini got 6 out of 11. But our average gap was smaller than the one obtained by Forini. For the U-slope, we also compared with Russo 2013, and we only got 1 optimal solution. This is really effective dynamic programming. And we got an average gap of 0.6, so it is also good. And from Sintra, it was also dynamic programming, and we also got only 6 optimal solutions. And again, for the 2-stage version, we also got 10 out of 17, and the gaps were also small. And for the unlimited fixed and weight, we got the worst results. We were not able to find any optimal solution. So what conclusions can be drawn? We propose a new MILP model for the single knapsack problem, and this could be used in 12 different guillotine problems. This model does not require the positioning coordinates of each item. And regarding the computational experiments, we performed, when comparing the different variants of the problem, the MILP performed better for the U-slope case. And we think that a good upper bound could improve our results, since probably we are in the optimal solution, but we don't know it. In the second set of experiments, when we compare with the literature, we think for the single knapsack problem, we outperformed the results obtained by Forini in 2016, and we got similar results as Martin 2020. For the slope and U-slope, the MILP has shown that it's not competitive, but it can be also improved by the bounds, for example. And That's all. I finished my presentation, but before thanking you, I also would like to upgrade the title of my presentation. I think if it was today, I would move it, instead of saying a general mixed integer programming model, I would say it is a highly flexible mixed integer programming model for rectangular guillotine cutting problems. So thank you. Questions? Thank you. Let me see. Need to stop sharing, otherwise I can see.
Tony has a question.
Okay, Tony, please.
Hello, thank you, Elsa, for the presentation. So I saw that you provide a very comprehensive comparison against many other methods, and I wonder, because of course that there is a different year as well on those publications, and you can approximate more or less the computer power if you wish, but no, I'm not so sure about the solvers, because the solvers provide another noise in that. So how you're going to address that?
Yes, it's really a question. At that moment, we would like to see how our model behaves, because if we have to implement all these models to compare, a nightmare. And in fact, we would like to see how it behaves in terms of the value of the solution and the gap. And I think it was on that. Of course, that to make it correctly, we should implement it in the same machine with the same solver.
No, that's not for the number of results that you have presented. That's perhaps not something that you cannot do. But I was wondering.
But this could be a good start to look specific to one problem and take the model and try to improve the model to that one and compare with the literature for that problem specifically. It could be a future work to do, of course. Okay.
Yeah, that makes sense. Thank you. Nice presentation.
Thank you. And I think Mateus also have a question.
Hi, Elsa. Congratulations for your nice presentation.
Thank you.
It's nice to see new models in cutting packing problems. I like new models, so congratulations. I'd like to hear about the linear relaxation of your model. I'm going to talk about that in my the next talk, so I'd like to hear a few comments about it, your approach.
It is a really nice question, but in fact, we have made computational experiments, but it was so long time ago that I'm not able to correctly answer your question. It is really a nice question, and it is something that should be included in the computational experiments to see if, in fact, the bounds could be improved on that side also.
Okay, thank you.
Thank you. I think I have no more questions. So our next speaker will be Mateus, and he's going to talk about the constraint two-dimensional guillotine placement problem.